Hey everyone, this video is about p-values. What in the heck is a p-value? You've probably heard of this at some point. They're ubiquitous in science, and maybe you've heard people arguing about whether or not we should care about them, whether or not they should be less than 0.05 or less than 0.005 or who knows what. But it's important to understand what exactly they are. To explain the concept, I'm going to use a very well-known example. It's just kind of a classic of intro stats courses. It's the lady tasting tea. If you want to learn more about this, you like thinking about this, there's actually a book that covers it in depth and actually goes into a lot of the history of some of this work and the people who did it. I confess I actually have not read it, but it comes very highly recommended by a lot of statistics professors. So I'd suggest that if you're interested. So this example comes from the early 20th century in England. We're in Cambridge at a garden party and people are having tea, as they would, of course, would. And a woman says to the waiter who comes up to pour the tea, "Oh, wait. Please don't do that yet. I would like to, finish this and make sure that there's no milk in the cup. I want it to be tea followed by milk and not the other way around." People are looking at her a little like, what? And she says, "Well, it tastes different. I can taste the difference." People are like, "How could you possibly?" There are some chemistry professors there. This is Cambridge, and the chemists say, there really couldn't be any chemical difference between those two drinks. Tea first, milk first. It couldn't possibly make a difference. So there's no way that you can taste one. Well, she says, "Well, no, I can. I can taste the difference." And so Ronald Fisher, arguably sort of the father of modern statistics, stands up and says, "Let's test this. This is an empirical claim." She says, "I have the ability to tell the difference." The chemists say, "Wow, no, nonsense. Nobody could possibly tell the difference." Let's test this claim. Let's run an experiment. Here's what we're going to do. We're going to make 8 cups of tea. And in these 8 cups, there will be 4 that are milk first and 4 that are tea first. The lady will not be in the room when we pour these. She won't know which is which. But then we'll bring her back into the room and we'll say, "Okay, identify the 4 that are tea first." There are 4 cups that are tea and then milk. You find them. Well, she could get anywhere between 0, 1, 2, 3, or 4 correct. But I don't know, suppose she got 2 of them right. Would that convince you? Would you think, "Oh, well, clearly she has some ability"? You can imagine her getting 2 out of 4 correct and then saying, "Well, sometimes I mess up, but clearly I'm getting at least them, right some of the time." But if she's just guessing randomly and she has no ability to tell the difference, well, then shouldn't she get at least 1 or 2 of them right just kind of by chance, right? Wouldn't it be sort of weird if she got literally none of them right? Wouldn't that actually be kind of improbable? In fact, it would be. And we can actually calculate the probability of each of these possible outcomes pretty precisely. So, assuming she's guessing completely at random, she has no ability to discern the difference at all, then what are the possible outcomes? Well, obviously there's only one possible way she could get 0 correct. There's only one possible way to get all 4 correct. But if she were to get 1 or 3 correct, there's actually 16 possible ways. There are a lot of ways of combining these different cups, guessing which one is which, that would lead you to getting either 1 or 3 correct. And there's even more that would get you to getting 2 correct. So again, assume she's completely guessing at random. She has no ability to tell the difference whatsoever. How likely is it that she would get 1, 2, 3, or 4 correct? Well, there are 70 possible outcomes. 70 is just the sum of this possibilities column, right? So it's just all of the possible ways that things could go. So suppose she gets 2 out of 4 correct. What are the odds of getting 2 out of 4 correct if you're guessing completely at random? Well, it's 36 out of 70, which would be about 51%. Right? So that's the chance, assuming that she's guessing at random, that she would get exactly 2 correct. It's almost a coin toss. If you said instead, what are the odds that she would get at least 2 correct, assuming she's guessing completely at random? Well, then it would actually be even higher because it would be 36 plus 16 plus 1 out of 70. It's about 75%, right? So it's more likely than not that she would get at least 2 out of 4 correct if she's guessing completely randomly, right? Suppose instead 4 out of 4 correct. According to the story, the way Ronald Fisher told it, that's actually what happened. She got all 4 of them. She nailed it. Well, the odds of doing that, assuming that you're guessing completely at random, are only 1 out of 70. That's about 1.4%. That's pretty unlikely, right? Like, I don't know. It's still possible that she's guessing randomly and this is just a weird fluke, but it seems like it's such a fluke, or it would have to be such a fluke, that now what we ought to do is actually reject our original assumption. Originally, we were saying, okay, suppose she's guessing at random, suppose she has no ability to tell the difference. Well, that would lead us to think that we've just observed something incredibly improbable. So what we actually would want to do probably now is say, no, we were mistaken before. Our assumption at the start was wrong. We're going to reject that, and we're now going to conclude we actually have sufficient evidence to think that she probably does have the ability to discern the difference. That, my friends, is a p-value. A p-value, formally, is the probability of observing results as extreme or more than what you actually observed, assuming the null hypothesis. The null hypothesis is the nuh-uh hypothesis. It's what these chemists were saying in the example. There is no effect of your experimental treatment or intervention. There is no correlation, no relationship, no difference, no nothing. Not a nuh-uh. If we assume that, then we can calculate the probability of observing what we observed or something even more extreme than that. And then that probability is our p-value. And then what we do is we say, if that probability is low enough, then we actually reject the null hypothesis. We reject the nuh-uh assumption that we started with, and we say, no, there is a relationship, there is an effect, there is a correlation, whatever it is. That is the basic concept of a p-value. Now, this lady tasting tea example is a fairly simple and straightforward one, but this same basic concept applies across all of the different kinds of hypothesis testing frameworks that people are going to use. You can scale this all the way up to a bivariate latent growth curve model with a time invariant covariate and blah, 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 blah. The p-value concept is the same. How you calculate it is going to become much more complicated. We're going to have to do all kinds of much more sophisticated things to get p-values, but that same concept of the probability of observing something as extreme or more than what you observed given the null hypothesis, that is going to be the same across the board. One last thing before we wrap up, and this is just the conventions around what is a low enough probability for us to decide we're going to reject the null hypothesis. And there's this norm or convention that's been adopted in a lot of different fields, including psychology, which is 0.05. That's the threshold. If the probability is lower than 0.05 or lower than 5%, then we reject the null hypothesis and we say there must be something going on. That is very much a contested norm. It's a thing that people are debating and discussing and thinking more seriously about. And so that's something to be aware of. But this just is the convention, and you will see this across many different journals and things. If the p-value is less than 0.05, then we treat it as something real that's going on. If not, we don't. And that's just the way kind of things work. In the next videos, we're going to talk more about how to apply this concept when looking at correlations in regression and ANOVA and t-tests and all kinds of different things.